Hi, this is Calculus 12, Chapter 6.4. We're going to be looking at exponential growth and decay. So the law of exponential change applies to many real-life applications where the change is proportional to the amount that's present. So some examples of this are compound interest, radioactive decay, Newton's law of cooling. So we'll be looking at these two. Resistance in a fluid, bacteria growth. We'll be looking at that. Depreciation, discharging a capacitor, damped oscillations, chemical reaction rates, and the amount of drug that's in the bloodstream. So these are all represented by the first order differential equation. dy dt is equal to ky. So the rate of change is proportional to the amount present, and we multiply that by coefficient. We can have initial conditions where y equals y naught, that's when t equals 0, or y equals yi, where t equals some initial time other than 0. So this is like slope-intercept for a line, and this is like slope point for a line. Okay, sometimes k is given. Other times we may have to solve for it, but we're going to solve for the general solution. We integrate both sides, 1 over y. We're just going to separate these two, just so it looks more like an integral statement. Integral k dt. So we want to separate. It's already separated, and integrate. This is an easy integral. Ln absolute value of y equals, oops, there's an equal sign there, and kt. And we have to add constant plus c. We exponentiate both sides with base e. So this just becomes absolute value of y equals e to the kt plus c. Exponentiate. And the next step, remove the absolute value. That makes this side plus or minus e to the kt times e to the c. So when we're adding exponents, we can split it up by multiplying powers. So y, and we can make plus or minus e to the c a constant. Okay, and we say a is equal to plus or minus e to the c. We can find a specific solution by plugging in ti equals yi equals a e to the k ti. So solve for k if not given. And you can say a equals yi e to the minus kti. Okay, it's negative because when we bring it over to the other side, it goes into the denominator. And when it's in the denominator, we can bring it into the numerator and negate the exponent. Okay, some notes here. K is a rate constant. If k is greater than 0, this is a growth problem. If k is less than 0, It's a decay problem. But you'll see that in some problems we want a positive k, so we make it negative k. Okay, let's look at our first example. Radioactive decay. And instead of having a base of 1/2 for the exponential function, we want to normally keep e as the base, and we want to keep k as a positive value for the function, so we write negative k. If tau is the half-life, that's a Greek letter, tau, and just to be clear, we don't want to use a half as a base. This is for pre-calc. And we want to use e, which is what we derived. And yes, you can use a half and get the answer, but you want to get used to using e as your base on problems that you can solve. That way, you'll be able to handle more difficult problems. If you don't use e now, you're going to run into a lot of trouble later. And this formula is derived by using ln and e. We don't have a half in here. So we have y naught e to the minus k tau equals 1/2 y naught. So the tau is like a t, but this part never goes above the horizontal line. Okay, so we can cancel out y naught. We can take the ln of both sides. So we have minus k tau equals ln 1/2. Divide both sides by negative tau. We take negative tau. K equals minus ln 1/2 over tau. And to get rid of the negative sign, we do ln of 2. Remember, this is changing the exponent to -1. And because this is used frequently in science, we have a special symbol for this. This is lambda. So let's look at a problem of how we solve this. And sorry, normally we say tau half, so that's half-life. Okay, so carbon dating, carbon-14 has a half-life of 5,700 years. Find the age of a sample that has 15% of its original carbon-14 proportion. So this is a little bit complicated. You have to know what the natural occurring ratio of carbon-14 was originally, but we're not going to get that complicated. Okay, so lambda equals ln 2 over 5,700. Okay, y of t equals e to the minus ln 2 over 5,700 times t. So y of t, we're trying to find t, and we want to find it equal to 0.15, and we have e to the minus ln 2 over 5,700 t. Okay, take the ln of both sides. Ln 0.15 equals minus ln 2 over 5,700 times t. So I'm just going to switch sides. T equals ln 0.15, and we're going to multiply by 5,700, and we have a minus sign there, and we're going to divide it by ln 2. Okay, because this is ln 2 over 5,700, we multiply by 5,700 over ln 2. Now it's okay to plug it into our calculator. Okay, if you forget the minus sign, it's not going to look right. So minus ln 0.15 times 5700 divided by ln 2. And we want to round it off to the nearest year. 15601 years. Please don't forget your units. This is years. Some half-life problems are quick, so they'll be in seconds or minutes, but for carbon dating, it's in years. Okay, so we're going to generate another formula, Newton's law of cooling. It's more complicated than half-life. So the change in temperature over time is equal to some constant factor, and we take the temperature and we subtract it by the ambient temperature or the surrounding temperature, such as room temperature. Okay, so temperature differential is going to be d dt, and we have the temperature minus the surrounding temperature. And that size remains the same. We let y equals the temperature at any time minus the surrounding temperature. Okay, so that just makes it a little bit easier. So now we're doing dy dt equals minus k y. We move the y over to this side, so we have dy over y. And we move dt over to this side, so we have minus k dt. We integrate both sides. Okay, so we have y equals e to the minus kt. So that's just like before, and let's just throw in a y naught. There's some steps there. Now we substitute our formula for y back in. So we have t of t minus ts equals t0 or t naught minus ts. Put that in brackets. And e to the minus kt. Okay, and we just want our formula in terms of t. So this goes over to the other side, and we have t of t equals t naught minus ts e to the minus kt plus ts. Okay, so on a test, you may or may not be asked to derive Newton's law of cooling. You may or may not be asked to derive the growth decay function. And in my class, you won't. You can just put these equations onto your reference sheet and use them. But it's a good idea to try to be able to recreate these equations. Okay, cup of coffee has just been poured and it's sitting at 97 degrees Celsius. After 10 minutes, it cools to 90 degrees Celsius. Room temperature is 20 degrees. How long will it take for the coffee to cool to 70 degrees Celsius? Okay, that's very hot. It's not very drinkable. I don't think anybody's able to drink it at that temperature. Okay, pick out the key features. Make sure you label them properly. This is T naught. This is T10. Okay, it tells us 10 minutes right there. This is TS. And this is a value we want to find, T of T. Okay, let's substitute things in. T of T equals 97 minus 20 e to the minus kt plus 20. Let's simplify this. This is 77 e to the minus kt plus 20. We know t of 10 equals 90. So what we're trying to do here is now we're trying to solve for k equals 77 e to the minus kt plus 20. Okay, we're just looking at this as our equation. This is just to help us set it up. Oops. We need to make this T10. Okay, move this over to the other side. Just like all our other algebra, let's just do a step at a time. 77 e to the minus 10k. That's probably easier to write. Coefficients come out front. 70 divided by 77 e to the minus 10k. Let's take the ln of both sides. This simplifies. Ln, we're going to divide by 7, 10 over 11, equals minus 10k. And then we just have to divide both sides by negative 10. So k equals ln 10 over 11 over 10. Okay, this divide by 10 does not go inside the ln. You can't bring a value from outside a function to inside a function and vice versa. And because we have a negative sign here, we can flip this over. Ln 11 over 10 all over 10. So that's our k. That's our setup. Now we can actually solve our problem. T of t equals, we're looking for 70 degrees. Please don't confuse this 70 with that 70. Equals 77. We can start off from here. E to the minus kt. So it's best to leave this as k because this is a lot to write out, and we'll substitute this value in for k later after we've done more algebra. Plus 20. So we have 50 equals 77 e to the minus kt. Divide both sides by 77, so 50 over 77, there's nothing common there. E to the minus kt. Take the ln of both sides. Minus kt. T equals minus ln 50 over 77, and k goes in the denominator. Now we can go ahead and substitute. Again, I'm going to get rid of the negative sign. Ln 77 over 50. And k equals this, so that means 10 comes into the numerator. And we have ln 11 over 10. Please leave everything as fractions. Do not use decimals. Otherwise, you'll round inadvertently and lose precision. We have this expression without any rounding, and we can plug that into the calculator. Ln 77 divided by 50 times 10 divided by ln 11 divided by 10. Okay, and we got 45.3 minutes. So you can see that there's a lot of steps, even though we're using the formula and we don't have to derive Newton's law of cooling. Be careful with your algebra at each step. Be careful about putting values in or out of functions. You want to avoid that. And if you're plugging things in on your calculator, make sure you have brackets to avoid a calculator error. And we're not deriving the continuously compounding interest rate, but it's good to note that this is the formula. Compounded every second, it would be roughly close to this. It's a theoretical topic and it's never used because they're not allowed to continuously compound the interest rate. But it's a good theoretical value to play with. And that completes this lesson.